Good morning, guys. So before we get started today, there's a few things that I wanted to share with you. Get switched over to the .com here and we can begin. Today is the 4th of September. We have some announcements. So first thing, WebAssign reached out to me. I got an email from them letting me know that the access, the free trial / temporary access, whatever, that's about to end. So if you have not purchased and input your WebAssign access code, you'll be kicked out soon. Not out of the class, not out of Canvas, but out of WebAssign. They weren't nice enough to give me an exact date or time, but the usual rule is 2 weeks, so I would probably expect Monday would be the day. So if you haven't sorted that out yet, if you're still using the trial access for free trial, temporary access, it's about to end. You really don't want to get kicked out. It can take a little while to get back in. There can be trouble. And the last thing you want is to fall behind right now because you can't get in and work on the homework problems. That would be really unfortunate because we're just getting to the place where we're starting to ramp up. So if you haven't sorted that out yet, if you haven't got your WebAssign access code, please do that. Please do that like today. Okay. If you're having trouble getting an access code, either because you can't find one or because they're too expensive or whatever it is, reach out to me, let me know. Sometimes the department has a few access codes they can give to students who are in especially financial difficulties. If the bookstore doesn't have one in stock and you go to get one, there are other places you can find them. So if you're having a hard time getting this sorted out, reach out to me. That way you don't end up in this situation where you get kicked out and have to wait a few days to get back in, because that can really be harmful at this point in the semester. You don't want to fall behind right now, and if that happens, it's a guaranteed thing to make you stumble. Not necessarily fall, of course, but stumble. And I don't want you guys to have to suffer through any of that. So just be aware. The free trial, the temporary access, that's ending. And I think it ends on Monday, but I'm not sure. They didn't tell me exactly. Another thing is to check out the modules page in Canvas. I added some new stuff. There's 2 new videos. I will show you here because I want to show you. So I talked about finding some animations to help you see what's going on with the dishwasher and cylindrical shell method a little bit better. It took some time, but I found some. What do you mean? You just displayed that, damn it. All right, for whatever reason, it didn't want to display there. But if you launch it in a new window, you'll see here. Now, I did look up the software that this guy is using here, but if you follow this link, it doesn't work anymore. So unfortunately, the software that he uses, it looks great, but we can't play with it. You can see he's doing the sort of thing that we always do. But what gets neat here is when he transitions over to this software. So I'm going to pause for a minute. You see here he's drawn the region. This horizontal axis, this is the x-axis, this vertical axis, this is the y-axis. And he's going to imagine rotating this thing, right? Just like we're doing. But he has this tool that allows you to see what happens when you rotate just one of the strips, like when you rotate just the strip rather than the whole region. And then he lets you see what happens when you rotate a bunch of strips. And I think it'll just help you see where everything is coming from. So there's your washer. And you can see that the inner radius of that washer, like we always say, is coming from the distance, the near end of the strip to the axis of rotation. And the outer radius of that washer is coming from the distance from the further end of the strip to the axis of rotation. So I'll let you watch that one more time. The inner radius comes from the distance here. The outer radius comes from the distance here. And then what's especially neat about this is he shows what happens with a bunch of strips. I'll just let this play for a second. There you can see the strip moving through the region. And there you see the solid being generated by all these little strips. When you integrate, you get this smooth object. But we're getting there via these sort of Riemann sum type things. So if you've been having a hard time seeing how this is working, I really like this video. I think it helps a lot. The other new one is a similar video for cylindrical shells. For whatever reason, it doesn't want to launch here, so just click this button. Here he's doing the same sort of thing, only now he's drawing a strip parallel to the axis of rotation, so he's using a cylindrical shell. I'm not saying a little bit of software will help you see what happens when you rotate just the strip to generate this cylindrical shell. And he does the same thing here where he helps you see a whole bunch of strips rotate at once. And you see how that sweeps out or generates this solid. Now, if you think of those strips as being infinitely narrow, then you get this smooth surface, the smooth solid. So if you've been having a hard time picturing what's going on in 6.2 and 6.3, I really want to encourage you to go to the modules page, scroll down past the review material. This is all that stuff that I encourage you to look at if you're having trouble with trig or basic integral stuff or needed some practice with U-sub or whatever. Come down here to the module titled Resources for Volumes of Solids and check out these two new ones that I added at the bottom here. Of course, these other things are great too. If you want to watch more examples, you want to see how Paul outlines these topics. Paul's Online Notes is a great website. Has all the formulas, lots of examples with solutions, nice pictures, all that good shit. And Patrick JMT is similar too. If you haven't looked at any of these, you might check out Patrick JMT. This is just a dude sitting down with a whiteboard solving problems. I don't think I would have survived Calc 1 or Calc 2 without Patrick JMT. So he's been around forever. I'll be clear about that. These are old videos. But it's good stuff. If you want to see more examples after class or outside of class, check those out. And definitely look at these visualization videos. They will be very helpful. What else? Oh yeah, no class Monday. Next Monday is Labor Day. I extended homework 2 to Wednesday, so it's not going to be due on a day we don't have class. I don't feel like that would be fair. But of course, I would love it if everybody had all that stuff done before Monday. That way you can relax and enjoy your holiday. And then on Wednesday, we'll come back and start working again. Okay. So that is it for announcements. Today, my intent is just to give you more practice with the stuff we've been doing. And I'd be happy to work any problems that you guys like. So are there any problems from the homework that you guys would like to focus on? I've got one in mind that I definitely want to do, but I'd like to start with whatever you guys would like to start with. So I'll go ahead and in the chat, let me know which homework problems are giving you the most headache. Which homework problems would you like to take a look at? Maybe while you do that, I'm going to grab some water. Okay. Number 5. All right, we can start with number 5. I think that is a disk washer problem. Let's see here. Yeah, where is that? There it is. Okay. So I'll write this down. This is homework 2, problem 5. Close this door. So here we're told to find the volume of the solid obtained by rotating the region bounded by this curve from negative pi over 3 to pi over 3 and the line y equals 5 about the line y equals 3. So this is interesting because our axis of rotation here is not one of the coordinate axes. So find volume, blah, blah, blah. I won't write all the words. Y equals 3 plus secant x, y equals 5. We're told that negative pi over 3 is less than or equal to x, is less than or equal to pi over 3, about y equals 3. Okay. So the graph of 3 plus secant x looks like the graph of secant x just moved up 3 units. So you have to remember what the graph of secant looks like. We had that area problem last week, so hopefully we remember from that. If that's 3, then here's 4. 3 plus secant x looks like secant x, but bumped up by 3 units. So the smallest secant x ever gets is 1. So the smallest 3 plus secant x ever gets is 4. And then he has this shape. Hey, Hamlet. The vertical asymptotes here are at negative pi over 2 and pi over 2. I'm not going to draw them in. Of course, secant is periodic, and he's got another thing shaped like that over here and another one over here. But we're going to pay attention just to the region that they're giving us. So negative pi over 3 to pi over 3 is like just this stuff. The line y equals 5, so this is 4. So I'm going to exaggerate this gap a little bit. We're going to call this 5 up here. And we want to rotate about the line y equals 3, which is down here. So like this. All right, so my region is this region. And just like in that area problem, when they gave us the negative pi over 3 to pi over 3, they're being kind. they're saving you having to solve for these intersection points. If you set 5 equal to 3 plus secant x, then you'll get secant x equals 2, cos x equals 1/2. So these really are negative pi over 3 and pi over 3. This point right here is pi over 3 comma 5. And this point over here is negative pi over 3 comma 5. So they could have not given us this, right? This is extra information that saves us time. I've got my graphs all drawn. I've got my region and my axis of rotation sketched. So what is the next thing that I must do?
Should you set up your integral?
Well, before I set up my integral, there's something else I need to do. Something else I need to draw.
The rotation?
What is it that we always rotate to find dv?
Strip.
Yeah, so we got to draw in this little differential strip. Since I'm using the disk washer method, should I draw my strip in horizontally, like this, which would be parallel to the axis of rotation? Or do I draw it in vertically, like this, which would be perpendicular to the axis of rotation?
Vertically.
Yeah, good. Remember, the disk washer method, you always draw your strip perpendicular to the axis of rotation. That's really what makes the two methods what they are. The one method, the strip is perpendicular to the axis of rotation. The other method, the strip is parallel. So my strip goes in like this. And now I need to figure out my big R and my little r. Little r is always the distance from the near end of the strip to the axis of rotation. And big R is always the distance from the far end of the strip to the axis of rotation. So I do have a page where I kind of show you all the formulas and I explain the definitions of each thing. I don't remember which class got to see that on Wednesday and which class didn't. Did you guys get to see that on Wednesday? Where I lay out the formulas for dv for each of the three methods?
I don't think that was us.
Okay, I'll do that. I'll bring that up after we finish this thing. So in order to figure out what little r is, I need to know the y value at this point. Little r is this y value minus this y value. Now this point is along the curve y equals 3 plus secant x. So that point is x comma 3 plus secant x. So the y value there is 3 plus secant x. What's the y value here?
Three plus secant x.
Well, here the y value is 3 plus secant x. But what about
Oh, there.
depending?
3.
Yeah, just 3. So little r is 3 plus secant x minus 3, which is just secant x. And big R is the distance from here to here. It's the distance from the further end of the strip to the axis of rotation. Now, no matter where my strip is, the far end of the strip is always up there along the line y equals 5. The bottom end of the strip moves. As the strip sweeps left to right, the bottom end of the strip tucks up over here. It's higher, down here, it's lower. But the top of the strip, the far end of the strip, is always along this line. So what's the distance from the far end of the strip down here to the axis of rotation? What's the y value up here?
5 minus 3, so 2.
Good, yeah, cap r is constant. Okay. Now we can write down our dv. dv is pi times cap r squared minus little r squared times dx, because this is a dx thickness strip, which is pi times 2 squared, which is 4, minus secant squared. Which means that v is the integral from negative pi over 3 to pi over 3, because those are the smallest and largest x values in my region, of pi times 4 minus secant squared x dx. And we're going to need a little bit more space here. I'll go ahead and move down. So I'd like to take a second and make sure everybody's comfy with why those r's came out the way they did. This is definitely the hard part. All right, this is the part that folks struggle with, and with good reason. It's kind of tricky. Remember, what we want to do is imagine that strip as sweeping from left to right through this region, and figure out how those distances change depend on where the strip is. If the strip's way over here, big R is still big R is still 2, but little r is quite large. If we're right here, big R is still 2 and little r is 1. If we're at an arbitrary x value, like right here, then big R is 2 and little r is secant x. Does everybody see? I'm thinking particularly about little r. Are there any questions about where little r is coming from? I want this distance. I know the y value here is 3 plus secant x. I know the y value here is 3. So 3 plus secant x minus 3 has to be that distance. And that is just secant x. I'm going to continue my volume integral over here. So that's pi times the integral from negative pi over 3 to positive pi over 3. 4 minus secant squared x dx. So I need an antiderivative. An antiderivative for 4 dx is just 4x. What's an antiderivative for secant squared x?
Tangent.
Good, tangent x, yeah. So this will be 4x minus tangent x evaluated from negative pi over 3 to positive pi over 3. So that's pi times 4 times pi over 3 minus the tangent of pi over 3 minus 4 times negative pi over 3 minus the tangent of negative pi over 3. Like that. 4 times pi over 3 is just 4 pi over 3. What is the tangent of pi over 3?
Square root 3.
Good, good. This comes from our unit circle. So this is 4 pi over 3 minus the square root of 3. And then from that, I have to subtract 4 times negative pi over 3. That's negative 4 pi over 3 minus, what's the tangent of negative pi over 3?
Negative square root 3.
Very good. And in fact, if we're being really clever, we could note that this function that we're integrating is an even function. So we could have gone from 0 to pi over 3 and multiplied everything by 2, right? This turns out to be the negative of this. So when we subtract them, everything just doubles. We'll be careful distributing our negative sign here. And what we see is we get pi times 4 pi over 3 minus root 3. Minus minus here makes plus 4 pi over 3. And then the 3 minuses here make another minus root 3. So we get pi times, I add the two 4 pi over 3's, I get 8 pi over 3. And the two negative root 3's, I get minus 2 root 3. And that's about as nice as that's going to get. So before we go any further, go ahead and find a page in your notes where you can write down these rules for the 3-volume methods. Here they are. This is what makes the 3 methods what they are. This is everything you need in order to solve all of these problems. And you do need to remember them as I'm giving them to you now. If you try to use formulas from the internet or even from the textbook, they will do you wrong sometimes. But these will never do you wrong. These always work. I'll break them down for you. The slicing method, that was the first thing that we learned. The way he works, your little differential volume you get by taking a slice of your total object and giving it a little thickness. You find the area of that slice, the area of the cross section, and you multiply by the little differential thickness. This could be a dy or a dx. So I'm going to write it as dt. And I'm just using t as the variable here because it could be y or x depending on your situation. So the slicing method, your differential volume is the cross-sectional area times a little differential thickness, and then you integrate that to find volume. The main reason I wanted to break this down for you is to highlight the differences between the disc washer method and the cylindrical shells method that we introduced on Wednesday. The disc washer method begins, you sketch your region, you sketch your axis of rotation, and then always the very next thing you do is you draw in your little strip. And that strip goes perpendicular. This symbol means perpendicular. So for the disc washer method, first you sketch your region, and always the next thing you do is draw your strip. Sketch the region, the axis of rotation, and then you draw in your little differential thickness strip perpendicular to the axis of rotation. So if your axis of rotation is like this, then your strip will be like this, which means there's a close end and a far end, because it's perpendicular to the axis of rotation. Big R is always the distance from the far end to the axis of rotation. No matter how they're oriented, no matter what variable you're using, big R is always the distance from the far end of the strip to the axis of rotation. You need to remember this. This is the only safe definition. And little r is always the distance from the near end of the strip to the axis of rotation. So again, because the strip is perpendicular to the axis of rotation, one end will be far away, one end will be close. Big R is the distance from the far end to the axis of rotation. Little r is the distance from the near end to the axis of rotation. So this is the disc washer method. And there's no simpler or smaller or cleaner way to write it. There are some formulas out there, but if you try to rely on them, they will do you wrong. This will never do you wrong. The difference between the disc washer and the cylindrical shells method is just these little parentheticals. The disc washer method, everything comes from drawing your strip perpendicular to the axis of rotation and then imagining rotating just that strip. The cylindrical shells method, everything comes from, well, first you draw your region, then you draw your axis of rotation, and then you draw the strip parallel to the axis of rotation. This symbol means parallel, just like this symbol means perpendicular. So for the cylindrical shells method, you always sketch your region, sketch your axis of rotation, and then draw in your little differential thickness strip parallel to the axis of rotation. Now, since your strip is parallel to the axis of rotation, maybe here's my axis of rotation, here's my strip. This end and this end are the same distance away from the axis of rotation. So there's not like two radii anymore. Now what you have is a height and a radius. That radius is the distance from the strip to the axis of rotation. There is no near end or far end. That strip is thought of as being infinitely thin, but it has a height. And then your little differential solid, dV, has volume 2 pi r, that's the circumference of the shell, times the height, times the differential thickness, whether that's a dy or a dx, depends on your situation. So this is your like Bible for 6.2 and 6.3. This is everything you need to solve all the 6.2 and 6.3 problems. The catch is making sure you remember this shit exactly.
So when you're taking the integral for the cylinder, do you still use, if you're rotating around the y-axis, would you still use the x values as the limits?
If you're rotating about the y-axis, well, you have to look at the picture. So if you're rotating about the y-axis or any other vertical line, then your strip is going to be up and down. So its thickness will be a little dx thickness. So you will be using x values. But if with the cylindrical shell method, you're rotating about a horizontal line, then your strip will be a horizontal strip parallel to that. And so you'll be using y values. So let's do some problems. Let's do a couple shells problems. I have a favorite shells problem here. And this is similar to, actually, let me see. I think one of your homework problems is actually very, very similar to my favorite one here. Yeah, this is good enough.
So on the homework, there was only one question about similar triangles. I just had a question if that was like actually going to be like tested on. I guess I don't really. Yeah, that I don't really remember doing that.
So we did do this exact problem in class. I just faced the pyramid pointing the other way. Similar triangles are definitely something you should know about. I would consider this to be a hard problem for something to put on a test because it does require a little bit more creativity. But I do want you to work through it. So if you're having a hard time with this, go back and look at our first video on volumes because we did solve this exact problem there. But an observation like this triangle is similar to the big triangle. If it wasn't in the middle of an otherwise already hard problem, I probably would consider that testable. I wouldn't think that's unreasonably hard. But here, this is in the middle of an otherwise fairly complicated problem. That's why we have all this help stuff here. But this would be a hard test question. If I were to put this on a test, I would give you some help like we do here. But let's come back to what we were looking at. Let's look at this guy. So this was, what number is it? 6, no, okay, yeah, 6. So we're gonna, got homework 2, problem 6. I'm gonna find the volume of the solid, blah, 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 where our curves are y equals the natural log of 7x. And what do they give us? Y equals 2 and y equals 6. And we're revolving here, about the y-axis. Okay, so this isn't a shells problem. 6.2, yeah, okay, we'll start with this one. Okay, about the y-axis. So this is actually a disk washer problem, but we can get started with this example. The curve ln7x looks a lot like lnx, only it's compressed horizontally by a factor of 7. So we still have this vertical asymptote. And then we want to smush the graph in by a factor of 7. That's going to make it look a little bit more like this. Maybe here is y equals 2. And maybe up here is y equals 6. And we want to revolve this around the y-axis. So my region is this region. What should I do now that I've got my region and my axis of rotation? What do I do next? What did we just say while we were looking at that formula page? First we sketch our region, then we sketch our axis of rotation, and then we draw in the strip, right? And we need to draw in our strip. So here I'm in 6.2, so I'm using the disk washer method. Should I draw my strip perpendicular to the axis of rotation or parallel to the axis of rotation? So this is a 6.2 question. All right, so we didn't have the shells method yet, so we're using the disk washer method. And if you look at the notes that we just had up, yeah, this should be perpendicular to the axis of rotation. So my strip is going to go in looking like this. Perpendicular to my axis of rotation. So here's my axis of rotation. Here's my strip drawn in perpendicular to that axis. Little r is the distance from the near end of the strip to the axis of rotation. And no matter where in the region that strip is, little r is always going to be 0. My region extends all the way to the axis of rotation. So there is no distance between the near end of the strip and the axis of rotation. Little r is equal to 0. But capital R is definitely not 0. Capital R is the distance from the far end of the strip to the axis of rotation. So that's this distance. Now the point right here where the strip hits the axis of, where the strip hits this curve, this boundary curve, is x comma ln of 7x. Because we're on the graph, y equals ln of 7x. So r is this x value minus this x value. What's the x value here along the axis of rotation? Good, 0, right? Because the axis of rotation is the y-axis. All those x's are 0. So here r is equal to x. But my strip's thickness is a dy thickness. So I need to figure out how to write the x value here as a function of y, which means I need to take this thing and solve it for x. So I take y equals ln of 7x and I solve for x. How do I solve that equation for x? Who remembers how to undo a natural law?
Put them as powers of e, or to e to.
Yeah. Yeah, you got it. I'll exponentiate base e on both sides. So on the left-hand side, I'll get e to the y. And on the right-hand side, I'll have e to the ln of 7x. E to the y is just e to the y, but e to the ln 7x, that's 7x. So 1/7 e to the y is x. In other words, this point right here, I could recharacterize as 1/7 e to the y, comma, y. They're the same thing. Now I've got my x value written as a function of y. So r is really 1/7 e to the y because that's what x is. And then I can go ahead and say what dv must be. The differential solid, you can draw it here if you like. It doesn't ever hurt to draw the picture. If I rotate just that strip, I will get a little flat disk looking like this. His thickness here is a dy thickness. He has a radius, cap r, and dv is always pi times cap r squared minus little r squared times the differential thickness, which here is dy. Now little r was 0, so this is pi times 1/7 e to the y squared dy. And that can be written more nicely. That's pi times, if you square 1/7, you get 1/49. And if you square e to the y, you get e to the 2y. So this is the nicest way to write dv. It's pi times 1/49 e to the 2y dy. And now I'm ready to integrate. V will be the integral of dv taken from where to where. Over what y values must this strip run in order to sweep out this whole region? I heard both of the numbers there. The smallest y value in my region, when the strip is all the way down here, that's y equals 2. And then I imagine moving that strip up, 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 up. And then the largest y value in my region, the largest I'm ever going to go is up here at y equals 6. So v is the integral from y equals 2 all the way up to y equals 6 of dv. So how does that shake out? Well, I've got this pi and this 1/49. I'll pop that out the integral. Pi over 49. And then what'll be left is the integral from 2 to 6 of e to the 2y dy. How do I do this integral? Does anybody remember this? We actually looked at this integral the other day. It was a little bit.
U sub to make the 2y go away.
Yeah, it's like a tiny, tiny little u sub. You could let u or z equal 2y. But it's such a small u sub that we want to get, it's one of those micro u subs, right? Because the differential is constant. If you let z equal 2y, then dz is 2 times dy. So these are so small that we want to get to a place where we can kind of do these in our head. I've said that a few times. And as we move forwards, that's going to be more and more important that we can do these tiny little u subs faster. an antiderivative for e to the 2y is 1/2 e to the 2y. And since I'm not really doing the u sub here, I just know what the antiderivative is, I'm not changing variables, right? This is still a y. So I'm going to use my original bounds. This is from 2 to 6. And this is one of those antiderivatives that you want to know, right? Like e to the ax has antiderivative 1 over a times e to the ax. We use it so often that you don't
Where
want.
did the 1/2 come from?
So if you wanted to work it out, what I'm using is this fact. I'm using the fact that e to the ax dx has antiderivative 1 over a times e to the ax. And if I'm writing it as an indefinite integral, it looks like that, plus c. This is similar to the forward derivative rule that you remember that uses the chain rule. This is a e to the ax. But if you wanted to write it all out carefully using the u substitution, I do want us to be moving past that. The integral from 2 to 6 e to the 2y dy, that substitution would look like this. Oh wait, no, this is 2, right? So 2 would go to 4, and 6 would go to 12. So this would become the integral from 4 to 12 of e to the z times dy is 1/2 dz. So that would be 1/2 integral from 4 to 12 e to the z dz, which is 1/2 e to the z between 4 and 12. So if you wanted to write out the substitution there, you could do it like this. But remember, what I'm wanting you guys to do is, hopefully you've had enough practice with these u subs now that some of these basic antiderivatives, like e to some constant times x, you can spot that that antiderivative is going to be 1 over that constant times e to that constant times x. So the way I would prefer to do it for a simple little tiny substitution like this is for you to know that this antiderivative is what it is. If that's too much, then that's okay. You can do it exactly as I was doing on the other page there, and you'll get the same thing. When we evaluate here, I can pop that 1/2 out. Pi over 49 will become pi over 49 times 2 is 98. And then this will be e to the 2 times 6 is e to the 12 minus e to the 2 times 2 is e to the 4. So the 1/2 is kind of coming from the differential in the micro u sub, or it's coming from our little tiny little backwards chain rule. Okay. So let's take a second, look at this thing and make sure we're comfy with it. It's kind of a somewhat tricky disk washer problem, because we had to go through this procedure here. Again, the saving grace everywhere in this is going to be remembering those definitions that I gave you. So in the disk washer setting, cap r is always the distance from the far end of the strip to the axis of rotation. Little r is always the distance from the near end of the strip to the axis of rotation. And you have to imagine that strip as moving through your region. Questions on this guy? Are we all comfortable with the antiderivative step here? Okay, if there aren't questions, then I'm going to move on. I would like to look at a shells problem. So again, if you didn't get those in your notes, here are these rules. Make sure these get in here. These are important, especially this understanding of where the R values come from in the disk washer setting. So I'd like to do one not so hard shells problem and then one harder shells problem. I'll take the not so hard shells problem from your homework. What do we have? No, we did that one. Let's look at number 10. So same stuff, find the volume of the solid generated by rotating the region bounded by y equals, they gave me 5 cube roots of x, so I'll use that. And then what were the other boundaries? Y equals 0, x equals 1. X equals 1. Oh, okay, interesting. And I want to rotate those about the y-axis. So again, knowing these graphs, hugely important. And I'm aware that it is possible to get to Calc 2 without having these graphs firmly embedded in your head. But there is no way to survive Calc 2 without getting them firmly embedded in your head. So please work hard to get there. The cube root function looks like this. Over here, it looks like the square root function. You've got a vertical tangent line, and then it continues over here like this. Although I don't really give a shit about this part because I'm only looking, let's see, y equals 0, that's the x-axis, x equals 1, that's right here. Ah, shit, that's ugly. All right, there we go. Here's the line x equals 1. And I want to rotate this about the y-axis. So my region is this region. And here, this is a 6.3 problem. I want to use the shell method. So I've got my curves and my region sketched. I've got my axis of rotation sketched. What is my next step?
Drawing the strip.
And in this case, will my strip be oriented like this or like this?
Vertically.
Vertically, right? Because I'm using the shell method, this needs to be parallel to the axis of rotation. So, okay, here's my strip. Coming in here, parallel to the axis of rotation. If I were to rotate just that strip about the axis of rotation, I will get a little solid that looks like this. Oh, shit. Oh, no, I've done something horrible here. What have I done? These lines cross. All right. So I'll get a little cylindrical shell. It's not the whole cylinder, the middle is hollow. It's like just the wall. Okay, looking something like this. The volume of that shell I can find by imagining cutting this and unrolling it. This wall thickness here, that's the thickness of this strip, which is dx. The height here, that's the height of this strip, we call it h. And the shell also has a radius, which we'll call r. R is the distance from the strip to the axis of rotation. And because we think of this strip as being infinitely narrow, there's no like closer or further distance, right? I think of the distance from here to here as the same as the distance from here to here. So I'm not worrying about the thickness of the strip contributing to my radius. If I cut and unroll that shell, I'll get a little box. Its height is h. Its thickness is very, very, very thin. It's dx, coming from the thickness of the cylindrical shell's wall. But its length is interesting. We have to think a little bit about the length. So what dimension of this shell is the length here? The height is definitely still h. This depth or width or whatever is still dx. But what is this?
Would it be 2r?
It's not 2r. So in words, what is it?
Circumference.
Yeah, it's the circumference of this shell. If you're looking straight down from above, this shell kind of looks like a circle. The radius is r, so what's the circumference?
2 pi r.
Mm-hmm. Good, the circumference of a circle is 2 pi times the radius. Okay, so now we're in pretty good shape. I'm on the curve y equals 5 times the cube root of x, so this point right here is x comma 5 times the cube root of x. So what is h? What's the height of this strip? It's going to be this y value minus this y value. The y value here is 5 cube roots of x. What's the y value here?
0.
0, yeah. So the height is 5 times the cube root of x. What about the radius? What's the distance from the axis of rotation to the strip?
Would it be x?
Yeah,
1.
it's not 1. 1 would be if the strip is all the way over here, but remember the strip has to move from over here to over here.
So yeah, I was gonna say 1 minus r, but that makes no sense.
Yeah, that would not make sense. So remember the horizontal location of this strip is the same as the horizontal location of this point because the strip is vertical. So whatever the x value is right here, that's what the x value is right here or anywhere else along this strip.
No, yeah, that makes sense. I got it.
Yeah, so this distance r is whatever this x value is minus this x value. This x value is just x. This x value is 0 because it's on the y-axis. So r here is just x. Now a word of warning. The height will not always be this function, and R will not always be X. You have to draw the picture and you have to think about it in the way that I described those things to you on that formula sheet. But this is a nice, easy problem. Everything comes out as simple as it possibly can be. So my dV, the volume of this cylindrical shell, it's easiest to think about it like this. It's the height times the length times the width. It's 2 pi r times h times dx, which is 2 pi times x times 5 cube roots of x times dx. And we can clean that up. The 2 and the 5 make 10. X times the cube root of x, what is that? That's x to the 1 times x to the 1/3. So we add those powers. 1 plus 1/3 is 4/3. So this is x, come on, 10, x to the 4/3 dx. So then v is the integral of dv taken from where to where? I have to imagine this strip as running all the way through this region. So the smallest x value over here, all the way to the largest x value over here. What's the smallest x value in this region?
0,
And the largest?
1.
Good. So that's the integral from 0 to 1. I can pop out the 10 pi. I'm left with integral 0 to 1, x to the 4/3 dx, which is a power rule. Not bad at all, right? To do this integral, I increase the power of x by 1, and then I divide by that new power. If I add 1 to 4/3, I'm thinking of 1 as 3/3, so that would be x to the 7/3. The 10 pi is going to come along for the ride. My antiderivative is x to the 7/3 divided by 7/3, and we evaluate from 0 to 1. This is the same as see, I can take my 7/3 out from the denominator, flip it over, so I'll have 10 pi times 3/7. And then here I'll have just x to the 7/3 evaluated from 0 to 1. When x is 0, this is 0. When x is 1, this is 1. So I'll just get 10 pi times 3/7, or 30 pi over 7. Questions on this guy? Feeling good? Okay. We have just a few minutes, and in these last few minutes, I want to show you how to set up a problem that I like a lot. It's the same problem that we looked at involving the natural log on Wednesday. the disk washer thing. Only now we're going to do it by shells. So let's find an integral for the volume of the solid obtained by rotating the curves y equals ln x, the region bounded by the curves from x equals 1 to x equals e about x equals -1. So here's my y-axis, here's my x-axis, here's the line x equals -1, here's +1, here's e, here's the vertical asymptote from the natural log. And here's the graph y equals ln x. Not perfect, but good enough. Okay, so you guys remember this problem, right? We did this with the disk washer method. You can also set this up using the cylindrical shells method. So if I wanted to proceed from here, what would be the next thing I did? I've got my region, got my axis of rotation. So next up we do what? I know it's Friday, I know we're all tired, but play along with me. What do we do next?
Draw the strip.
Draw the strip, right? Do I draw the strip vertically or horizontally?
Vertically.
Vertically, because we're using the shells method, it needs to be parallel to the axis of rotation. Now you remember last time we did this, we had to come in and recharacterize a point. We had to do a bunch of algebra before we could get where we wanted to be. But this time, things are going to be cleaner. This point right here where the strip meets the curve is x comma ln x. And if I rotate just the strip, I'll get a cylindrical shell. I'm not going to draw the shell. I want you guys to tell me what is the height and what is the radius.
The radius should be 2 plus x, right?
Mm,
So 1 plus x, excuse me.
yeah, 1 plus x, right? This distance here is 1. This distance here is x. So r is 1 plus x. Yeah, very good. Does everybody see that? The horizontal distance from here to here is x because the x coordinate of this point is x. So this total distance is x plus 1, 1 plus x. And then what about the height?
ln x.
Yeah, the y value down here is 0. The y value up here is ln x. So the height is ln x. And then if you remember the formulas for dv, you don't have to do that whole draw the thing, cut and unroll. You can just write dv down right away. dv is 2 pi r times the height times the differential thickness of the strip, which here is dx. That's 2 pi times x plus 1 times ln x dx. So what would be my volume integral then? V is going to be the integral of dv taken from where to where? If I want my strip to run everywhere through this region, what's the smallest x value I have to consider?
1 to e.
Yeah, good, from 1 to e. So go from x equals 1 to x equals e. So my volume integral is 2 pi integral from 1 to e x plus 1 times the natural log of x dx. So the volume integral here is much easier to set up using the shells method, right? We've done this problem before using the disk washer method, and we got e plus 1 squared minus e to the y plus 1 squared. It required a lot of algebra. But then we could do that integral. That integral wasn't too tough. This integral you guys don't know how to do yet. So this is why I like this to be my last example problem from this section, because the next section we're going to cover, section 7.1 in the textbook, is where you're going to learn how to do this integral. This requires something called integration by parts, which is like if the u sub is a backwards chain rule, integration by parts is a backwards product rule. Look at this function. If I wanted to differentiate this function, I would definitely need the product rule, right? It's this thing times this thing. So to integrate it, I would use a backwards product rule. We don't know that yet, right? So I'm going to teach you starting next week. How we're doing for time? Yeah, right on time. So starting next week, I'm going to show you how to do integrals like this. Unfortunately, next Monday, we don't have class, right? Next Monday is Labor Day. It's an important holiday. I recommend everybody research it and pay attention to where it comes from, because labor unions have done a lot for working people in this country, myself included, and probably will do a lot for you in your lifetime as well. So enjoy the holiday on Monday. And then next Wednesday, I will show you not just how to do this integral, but how to do lots and lots of other integrals that previously we never could do. Between now and then, though, I want you to practice setting up these problems. So the homework is the homework. It's not terribly hard. There are a few problems in there that you might find tricky. Before I let you go, I want to make a quick comment about this guy. The integral you're going to get when you set up this guy using cylindrical shells is a hard integral. You're going to need to really take your time with it. First, you want to picture this solid as a solid of revolution. You have to find some way to think of this as some region having been revolved around some axis. That's not too hard. If you want to get a torus like that, you can take a circle like this and spin it around like that. Let me show you. Right? If you were to take this region and revolve it around the y-axis, then that would give you a torus. I do want everybody to go through the process of setting up this integral. So I'm going to give you a little bit of help here. If this circle is going to be centered at positive r comma 0 and have radius little r, then the equation for that circle is x minus cap r squared plus y squared equals little r squared. And if you solve that for y, you'll get plus and minus the square root of little r squared minus x minus cap r squared. So this is the equation of this circle. So if you wanted to set this up as a shells problem, you would come in here and draw in a little strip vertically. Then you would need to find the height of the strip. That's going to be this times 2, right, without the plus minus up front, because the upper point here comes from the plus, the lower point here comes from the minus. So that height is the plus minus the minus, which is 2 times the plus. So this distance that we normally call r, that's just going to be x, because this is happening at x. And this distance that we normally call h is going to be 2 times the square root of r squared minus x minus r squared. Like this. I think one of the things that makes this problem a little bit confusing is that they're using the symbols capital R and little r already. And our formulas have those symbols in them, so it can be confusing. But I think this should be enough help to get you started there. And then once you write down the integral, I would recommend stopping for a minute and asking if there's another way to think of that torus. So my art is not very good. I will do my best. Here's your torus. The cross section here is circular with a radius little r. If you imagine taking a very hot knife and cutting this torus, you could unroll it into a tube. And the volume of this tube is much easier to find than the volume of the torus directly. The cross section here is still a circle of radius r. So in other words, if I wanted to find the volume of this torus, rather than thinking of it as a solid of revolution and attacking with cylindrical shells, I would do slicing. So I'll let you think about how to get the volume of this thing. That's very, very easy. But I still would like you to set up the integral you get from thinking about it like this. And then if you get stuck on that integral, that's okay. You can come by my office hours or shoot me a Canvas message. I'd be happy to talk through it. Basically, you're going to have to make a substitution, then split the integral up. One of the integrals will be easy. The other integral is going to require a geometric interpretation. So remember back at the end of Calc 1 when you were asked to calculate the definite integral by recognizing it as the area of some solid or some region that you knew from geometry. You'll have to do something like that when you get to that last problem. But if you're looking for the answer, right, and there's nothing wrong with coming up with a clever, better way to solve the problem, this is the clever, better way to solve the problem. So you take your torus, you slice it, and you kind of undonut the donut, right? A donut is like a tube that's been joined. Undonut the donut, unroll it, and you'll find that that volume is very easy to calculate. So that's as much hint as I want to give there. That problem is a little bit tough, but it's well within reach for you guys. Look at the textbook if you get stuck here also. The textbook refers you back to section 6.2 where they give you another way to do it. And then finally, if you set up the volume integral here correctly, but you're having a hard time doing it and you don't want to do this, I wouldn't blame you if you asked Wolfram Alpha to help you with that integral, because again, it is a hard integral. Not unmanageable, but a little bit tricky. So this last problem here, God damn it, why isn't my alt tab working? This last problem here, I acknowledge is hard if you do it the way they say. Try setting it up the way they say, but also try other stuff. It doesn't need to be a hard problem. Okay. Any other questions for me before we sign off for the day?
No, sir.
Everybody else feeling pretty good? Hanging in there? Yeah. Okay. All right, so then I hope you enjoy your weekend. Remember, Monday is a holiday. The current homework will be due on Wednesday as a result of that. Try to get it done before then, of course. If you get stuck on anything, feel free to reach out to me. I do have an office hour this afternoon. And if you want to talk to me outside the office hours, you can always send me a Canvas message. We can arrange a separate meeting time, or we can just talk through Canvas messages. But that is it for today, guys. Starting next week, we're going to talk about integration by parts. So we will be changing our focus pretty dramatically. We'll be stepping away from this geometry and looking more at just straight analysis. Alrighty, I am going to go ahead and end the meeting here. I hope you guys have a lovely rest of your day. And again, if you need help with anything, just reach out.